for staying this long. I know it's getting late. It's an honor to speak to you and have this opportunity to present information that I know knowledge of. So we're going to talk about freezing water lines in the U.S. I'm going to focus on Alaska's because that's where I'm from. And what the technology is that we use to prevent water lines from freezing. And it goes from burying lines really deep to using heat trace or other forms to get heat into the system. Sorry, I'm still recovering from laryngitis. So first about me, I got my engineering degree from Montana State University. I went there for skiing, came out with my engineering degree. So not by accident, but on purpose. I started out my career designing roads, streets, wastewater pipes, aircraft stands, and really good civil projects. But I got kind of bored with the design side of things. I like to get my hands dirty. I like to get into the field. So I went up to the North Slope and I built ice roads and ice bridges and gravel pads and those things. I got some really good experience on talking across the line from design to construction and getting that experience. And that helped me build where I'm at now at Anchorage Water and Wastewater Utility. And I edit our standards, so our design and construction standards, as well as our specifications. So I'm using all the resources that we talked about here to combine it into our own manual so that we have a very strong and resilient system. So that line of this talk is we're going to go over Alaska-Korean comparison. I think it's important to see why Alaska is special and how you can use some of this information in what you do. And permafrost, because we're talking about frozen water lines. Alaska is very unique. It's a very large state. So we have a lot of differing conditions to talk about. Frozen soil concerns. Ice does a lot of weird things to soil. Preventing heat loss, adding heat, thawing, and why condition assessment is important. And then construction impacts. So first of all, Alaska has a population of 730,000. Korea, 51 million. The area of Alaska is 17 million square kilometers to 100,000 square kilometers. Our northernmost latitude is 71 degrees, and southern is 51, compared to Korea at 38, 33. So we have a huge difference in temperature. Up on the North Slope, up here, we have 5,300 degree freezing days. So the ground up there stays frozen all the time. And we'll go into that. And we have some warmer areas down here in the southeast. When you compare it to Korea, it's much warmer here. So you don't see a lot of frozen water lines here. So permafrost. What is permafrost? This is soil that never thaws. Okay? So it's always frozen. We have continuous, which means more than 90% of always frozen soil. So how do you put water lines in frozen soil and keep your water lines thawed? And then you get into some really complex problems with discontinuous permafrost. Because when you add heat to the water to keep it thawed, you're also thawing the ground. And when you thaw the ground, it becomes unstable. So you've got to plan around that. So you cause impacts to your environment that's going against your pipe system. You got sporadic, you got isolated, and you have absent. Anchorage is here. We have very little permafrost, but we do get very cold. Oops. So let's talk about burial depth. That's how we protect our pipes in most areas, is we bury it below the frost line. But in our coldest location in Univ, it's buried at 0 feet. And we just add heat to the system. In Selawik, it is literally above ground. In Fairbanks, it's 4 feet. Now these are all really cold places, and you see us keeping it up into the cold. We're just adding heat, which takes energy. It's very costly to run these systems. And not only that, they're off the road system. So we have to innovate to counter the problems of not having a road system having sporadic access with limited operators, limited response time. As you move down into Anchorage and Kenai and Soldotna, you're down to 10 feet because that is our frost line. That's how far the soils get frozen. And then you get warmer down here, like Seattle and Juneau. So it's only buried 4 feet, which is pretty typical across the states. I keep it the wrong button, I'm sorry. So with depth of bury comes cost. I did a quick conversion. One of my last projects was 30 million won per meter. Okay, that was $8,000 a foot to replace that line. So it becomes very critical that when we design our systems and we put stuff in the ground, that it lasts a very long time because it's very costly to replace the infrastructure. So Utipagik, they changed the name from Barrow. I said it was buried 0 feet up there. It is buried, but this conduit here is really up at the surface and in the active zone. So this is the zone up here where it actually does thaw. But we put our water, our sewer, our power, all utilities in one bank because it's cost effective to put it there. And you have to ensure that whatever heat you're adding here, you protect the ground down here from thawing. So there's a lot of thought that gets put into heat exchange, and then in the wintertime for the cold to come back in and freeze it so that it stays stable and your pipelines are solid. But down the Selawik, where it gets to be more discontinuous, it's all above ground. So these are all sewer, vacuum sewer lines and water lines that are above ground, and they're insulated, they're heat traced. And because it's discontinuous, that when you're adding heat to the water system, you can melt the ground and it will stress out the pipes and then will break. So you want it above ground, you just want to keep it heated. Again, it's very expensive to heat water all year round. In Fairbanks, they developed another system. So they put heat into their water system by pumping it around. And so it's very unique in that the water comes in this direction and it's forced into the service line this way, into the building, and then they pump it back out. So you have water always moving, just like in a creek. You know, when it's really cold outside, the creek's still moving underneath the ice. Well, it's the same way in Fairbanks. So they add their heat by pumping the water around and using insulation to keep that heat to the inside the pipe. Frozen soils and earth pressures. So in Anchorage, we've got really good gravel, we've got really horrible silts, and you've got high groundwater. So you have a lot of water to create frost. And what that does is it can move in some of those boundary zones and cause deformation of the pipe. So just we're talking about resilient pipe systems, we need to have a pipe system that can handle movement just from the annual event of freezing and thawing. We have a lot of cast iron pipe that breaks in the springtime because of this frost action. So frost jacking is where the water in the soil around your pipe, because we have a lot, like fire hydrants, come up out of the ground, and the water freezes and pulls that pipe up. So we get a lot of frost jacking. We want to try and avoid that by wrapping everything in polyethylene. We have 3 layers of polyethylene, so it slips on the pipe, it slips on the individual layers of polyethylene, and it slips in the ground. So this is our hydrant risers. That's 10 feet, and you don't want to add anything to the riser. No joints here, so that's a solid piece of pipe. And then we had a problem in which the manufacturer changed their shoe design. And it wasn't handling the frost jacking that was going on, and we were going to see a lot of failures here. So we worked with that manufacturer, and they changed their joint. And so that's working with industry. And going back to having those mid-flanges, that's the point where frost is going to grab and just pull that hydrant right out. We also use a lot of insulation. You can add insulation after the fact, or you can add it in the manufacturing process. So in this case, what you have here is the HDPE outer liner, really thin wall. You have polyurethane foam and the interior 8-inch pipe. And in this case, I needed to restrain it because it was a water line. We were going through a casing, that's why we have a casing spacers there. Another really interesting project, it wasn't mine, it was one of my good friends, is that we were looking for ways to save money for our customers. And we did it in two ways. One, through the power company, and we were talking earlier about working with other industries. So in this case, our water comes in at 5 degrees Celsius. And the power company has a lot of excess heat they need to get rid of. To do that, they were running the heat through a radiator, and the radiator was evaporating the water. And they were using our water, so we're charging them for every gallon that went up in the air. So to reduce that, we took that heat and we put it back into the system, and we raised the temperature to 13 degrees Celsius. What that did is that saved money for the power company. They didn't have $500,000 a year going to make up water. Water heating expenses across all the water heaters of our 270,000 residents was reduced, because now the water's coming in at 13 degrees Celsius. And so you have that delta T, so you're not using as much natural gas. Your CO2 levels go down for heating it. And our main repairs, we estimate that maybe it'll go down because we're not dealing with such cold water and freezing conditions. So we heated our water up, and we had a benefit. So this is a picture of the plant. This is the power plant, and you can see all of this water. That's our production water. That's our drinking water going up in the air, and they're paying for it. And so this has been reduced because we're now taking that heat and putting it back into the system. So working with another utility. So, but as much as you try, you do end up freezing water lines. And so one of the areas that we don't like to use it, but it does happen, is that you connect a welder and you run a current through the line. And the resistance heats up that water enough to break up that ice chunk, so then you get water flowing through it, and you thaw out the ice bulb or wherever it is that froze up the water source or the main. And that's only good on copper lines or ductile iron lines, because those are the only ones that we have continuity wires to. One of the big things in 2012, when we officially adopted PVC, was that we were really worried about how do you thaw a PVC water main or a water service, because PVC melts at 85 degrees Celsius and the steam comes in at over 100. So is that steam going to cause more damage? That was a huge concern for us. And it turns out that it was not such a big concern. This is actually one of our trucks here, because we have to go in and thaw the ground before we can dig in it. And so we steam thaw it. And we don't want to put that steam right on the pipe and go right through it. We're already there digging it up, so we replace that section. But the collateral damage we were really worried about. And over the years, we've seen it not come to a problem. So it's been a good one thing we don't have to worry about as much as we thought. Adding heat, there's a couple ways to do it. You do it with electrical resistance tape. Problem with that is the heating tape only has a very short-term life, maybe about 5 years, so you've got to go in and replace it. And some of these lines are buried. It's very expensive to go in and replace. Other places have some glycol lines, or you have some water lines where you're always putting hot water in. Those are a little more rare. So we're 10 feet deep in Anchorage. It's very critical that we have a good idea of what our system is. And to do that, you have to know what the condition of your system is. And there are some really good technologies that are out there that are being developed to understand what the conditions of those pipes are. One summer I got a project to do a lot of condition assessment, $2 million worth of work. We dug up lines, we sandblasted them to see what pitting was, and did some analysis on the pipe. Along with that, we did some other testing of it, Pure Technologies, where they have a smart ball go through the system, and it tells you it can hear leaks. And then the Echologics, that sends sound waves through the pipe, and it'll tell you about what your wall thickness is left. So it gives you an idea of whether or not you're at 90% of the life or 25% of the life. And there's limitations in all of this. So you gotta kind of read the tea leaves to know what the condition of your system is. It's not economical to do the whole system, but when you get an idea about, where bad areas of town are, you can go focus your money and your effort on those areas. You can be more responsible with the funds that you do have. And I also got to put in this neat little thing, a sea snake, a very sensitive piece of equipment. You bring it through the line, and it'll tell you the wall thickness of ductile iron. So we did a great program to get an idea, because we have a very strong asset services section that brings all that data together, brings what the soil conditions are in Anchorage, and we now have areas that we know are very prone to corrosion and prone to movement and breaks, and so we can focus our money and our effort in those critical areas. So sometimes cold is good. Here I'm working at the railroad, and because the railroad shuts down in the wintertime because we have a lot of tourists that come in the summer, I went out and got a project installing a liner in a large diameter main. So sometimes the cold can be good. Winter construction, we don't do a lot of it. It gets to be really complex. One, you're trying to put in a water line, our groundwater is really high, so you're trying to find a place to discharge all of the groundwater. You're trying to keep things warm. You're thawing the ground. So right here we have a glycol heating system that's thawing the ground just so we can dig it. Because again, that frost goes down to 10 feet, so digging through 10 feet of frozen soil gets to be rather expensive. Now our lines are really deep, and so I borrowed from the power industry because they have a lot of remote tools. You don't want to be grabbing onto a power line, you want to be further away. So they had some great tools that I could go out and reach into the ground 10 feet down with a small hole. Now you can imagine 10 feet down, if you're digging it up, your trench is huge, and you're digging in people's front yards to replace key boxes. So now what we do is we sink a 2-foot diameter caisson right over the key box, and we use remote tools, or long sticks, and we put anodes on. It all came from, those tools came from the power industry because they're operating at a distance from those power lines. And so we're able to adopt their technology and apply it to ours and not have to go through and ruin people's days tearing up their yards. Because this was the start of the hole, this is us replacing a key box, and then this is after, all within 3 days. So, and the cost to do this was just slightly a little bit more expensive than open cut, but the public perception was astounding. They have a yard again. And with that, I will take questions.